Great. Thank you so much, Ali. So hello everyone. Thanks for coming on a Thursday night. Today we're going to talk about CUDA. We're going to see some basics of it. So this is the first week in a series of few workshops that are going to follow basically the same topic. Um, yeah. So I guess before we start with the content and the topic and like what actually CUDA is, kind of starting to build up, it is in order if I sort of introduce myself. So my name is Riyad, and I stand here today in the capacity at UTMIST as an academic director. And I also, well, I'm studying at U of T as a computer science specialist for the third year, but I'm right now on my co-op term and I'm working for AMD. So my company wouldn't be too happy if they knew that I'm presenting CUDA, but CUDA is I think, very valuable tool in a programming language and library and platform in general that opens the door for so many things, and especially in the way that the world is evolving with the AI and the extreme usage of like accelerated compute like GPUs. It is really important to understand how CUDA works. And once you understand how CUDA works, you can pretty much transition your way into some other similar platforms like ROCm. ROCm is another one of the examples that is developed by AMD. So yeah, without further ado, um, it's good that we have few people, so we will be able to just have a little conversation at times and question and answer and whatnot. So let's start with understanding what performance is and why it matters in compute. So I want to start by saying every computer operation takes some time to do what it needs to do, and it moves around some data. And there are two key factors to determine how fast things run, right? The first is latency, which is in the simplest term, how long it takes to start and finish one operation for a computer. And we're going to expand on this definition. We're going to give some examples and everything. So don't worry, this latency and bandwidth is coming up. And bandwidth means how much data can move per second. And they're both critical in the understanding of comparison between CPU and GPU design and understanding how it affects how fast your programs execute. So to solidify this with an example, loading a video versus streaming multiple videos at once, both are limited by how quickly data travels and how much can move at one time, right? It is a graphics operation. So let's talk more about this terms and give some more examples. So as we said, the latency is in short the wait time, right? It is the delay between when you request a CPU or a processing unit to do something and the time it takes for it to complete it. It measures basically that. And the units that are used for this concept is nanoseconds or milliseconds. If we have a high latency, that is usually not a good thing, which means the CPU takes a lot of time, or whatever processing unit you're using takes a lot of time to respond and give us back what we requested. But low latency is always more ideal and what we are striving towards, and it means faster response. And to again strengthen it with an analogy, think of latency like the time it takes for a pizza to arrive after ordering. And even if the pizza place can make 100 pizza an hour, right? If the time it takes for any pizza or a group of pizzas to be delivered to your doorstep is 40 minutes, well, that's high latency, right? No matter how many pizzas you order, it's going to take a lot. So some of the examples, for example, when we talk about latency in the actual computing world is, for example, CPU accessing cache memory. It is 1 nanosecond latency. CPU addressing dynamic RAM, random access memory. It is 100 nanoseconds of latency. And GPU accessing global memory, that has a higher latency. But it is, well, we're going to talk about it more in detail, but it's compensated by running many threads simultaneously. So something called hiding latency happens here. And there's a little pyramid right on your right side, and it shows basically sort of the hierarchy of how different components inside your computer, like how much time they take to communicate with each other or get instructions and complete their task and deliver their basically output to a CPU as you go down or up the pyramid. So yeah, bandwidth on the other hand, it's the flow capacity, right? The definition is bandwidth is the amount of data that can be transferred per unit time. And in other words, it measures how much work can be done in parallel. The unit that we use to describe it is gigabytes per second. And it's high bandwidth means high bandwidth in this case is ideal, unlike latency, because it means we can move a lot of data at once, right? It is the ability of the pizza delivery store to make as many pizzas as possible when you request, right? How much their store can afford to basically make pizza in one go or in parallel with each other. And yeah, so a few again examples is for example, if you were curious about the memory bandwidth of this typical CPU, that would be 50 gigabytes per second. And the GPU memory bandwidth would be 900. That's significantly more. Speaking about modern GPUs here, right? Like AMD's Radeon series or NVIDIA's GeForce series. And GPUs rely on high bandwidth to feed thousands of parallel threads efficiently. Again, this might sound a little bit of like too much information for now, but we will talk about each one of them separately in coming seconds. So let's summarize everything that we have sort of discussed so far. Latency is the time to take that's taken to serve a memory request, and bandwidth is the rate at which data can be served from memory. If we think about it as some sort of flow of water coming out of a pipe or a sink, latency would be how fast it comes out of the pipe, and if you want to basically increase that latency, or sorry, decrease the latency, you need more water pressure, and the bandwidth is how much flow is coming out of the tap, and you need to increase that, you need a wider pipe. And now let's talk about this specific processing units. So to introduce CPU formally, CPU is the general purpose brain of your computer. It is essentially designed for low latency, right? It is highly flexible in tasks. It is optimized for sequential or lightly parallel operations. It contains a small number of very powerful cores. Often it's between 4 and 16, but this number has been going up recently. And it's really great for operations like operating system tasks, running application, branch-heavy logic, like if statements, decision-making, and it reacts very fast to single tasks. And CPU, again, to demonstrate that with an analogy, is like a skilled chef who can handle complex recipes one at a time with great precision. So to put this in words and kind of summarize this slide is think of it as a a processing unit that has few but very powerful cores, right? And those cores are able to complete very like complex sort of executions that require, for example, some complex logic like if statements and predictive compilation and whatnot. CPU is good for that. And one very important detail is that because we have fewer cores at play, if we receive like a high number of tasks or a high number of requests at a time, well, because we cannot, we don't have too much concurrency potential, we will have to execute them in like consecutively, right, in sequence. So GPU, on the other hand, it's another another version of a processor, but it's more specialized, and it's specialized for massive parallelism. So remember how I said CPU has few but very strong cores. GPU in this case contains thousands of smaller and simpler cores. It is optimized for performing same operation on many pieces of data at once. It prioritizes high bandwidth over low latency. So originally the GPU was GPUs were built for rendering graphics, but now it is heavily used for AI, deep learning, operations like matrix and tensor operations, image and video processing, simulation, scientific computing, and whatnot. So if our CPU was one highly skilled chef that could do a lot of great, could do make a lot of great food, GPU is like an army of cooks, each doing a tiny part of the recipe at the same time, not as seasoned or experienced as the one that we have in CPU. So to put them side by side, so CPU has 3 or 4 to 16 really strong bulls or oxens that are working for it. And GPU is many more chickens that are obviously way less powerful, but there's just so many of them. So this, I think a picture does a good job in giving you a good summary of that. Yeah, so this is pretty much everything that we have talked so far. Architecture-wise, the point about the course, and the strength-wise, at GPU, we are looking at throughput, right? That's what we are trying to prioritize, meaning we are trying to do a lot of work per second. Yeah, so there's the question.
Yeah. So what stops us from getting like hundreds of oxygen in the process?
Right. So when we have too many, so first of all, there is the issue with the size, right? The amount of space that each core is going to take in CPU is significantly larger than the single mini cores that we have at GPU. It needs more resources around it. It needs more cache. It needs more memory and some other of the factors. So that's why there's a trade-off between them where we either have many cores that are not as powerful, but there are so many of them, or the few ones, but they're pretty strong. Yeah, and yeah, all of these points will be talked about in the coming minutes and over the slides. But that was a good point. So we talked about AI, we talked about machine learning. So training a neural network requires multiplying huge matrices, as you know. So each CPU might compute one piece at a time. It is fast per step, but there is a very limited throughput, right? Because the number of cores that does this operation at a time is not too many. But GPU computes thousands of pieces simultaneously, finishing it much sooner. And in the example of again AI or machine learning operation, neural networks to basically use them, the underlying operation under them is like as simple as additions. Because when we talk about, for example, multiplying two matrices, I just remember from your linear algebra courses or whatnot, it really is about going through one by one the entries of the matrices in a specific order and just multiplying them with each other or really adding them with each other. And because addition is such a simple operation to do, but we have to do too many of them, right? If our matrix is pretty large, a GPU becomes sort of the most ideal tool whereby we can do it. So yeah, to sort of recap, the CPUs are designed to minimize latency, and they work fast on just a few tasks. And to achieve latency minimization, the majority of the area of a CPU is going to be dedicated to very sophisticated control logic and on-chip cache. So this design that usually works very well for general purpose programs, such as running like operating system and whatnot. But the CPUs are designed to minimize the latency, and the GPUs are designed to specifically maximize the computational throughput. So kernels. Let's talk about the kernels. The kernels are basically the functions that are run on the GPU. Um, when remember in Python and other programming languages that you might have used before, the function that does all the operations, right? We are calling it function. If it's a part of a class, it's a method. So this specific term, kernel, is what we're going to use if you're able to run that function on the GPU. Threads are basically the most basic threads of execution or units of execution, and think of it as the kernels or like the functions that are running on GPUs. They're going to be executed as many parallel threads. So two main pieces of hardware in the CUDA programming is well, CPU and GPU, right? And the CPU together with the computer's RAM is referred to as the host. Similarly, GPU, similarly, the GPU together with its own dedicated DRAM is called device. So when I say host from now on, please think of it as CPU. And when I say device, think of it as the CPU, GPU. So yeah, the problem, the CPU is very good at running serial problems, right? The problems with the CPUs is if they run into a portion of the code that is massively parallel, this part of the program will likely cause a bottleneck, right, in the flow of the program. And GPUs are very good at running a part of the program that is very parallel that we want. So we want to offload these massively parallel portions of the code onto the GPU. Using the host and device together is termed heterogeneous parallel programming. And this is where the CUDA comes in. CUDA is the heterogeneous parallel programming language that is designed by NVIDIA. And it's simply a C programming language with a set of extensions that allows for the host and device to work together. In the CUDA programming model, the host is in control of the program. For the most part of the CUDA program, it will run just like a traditional piece of software, just like a traditional piece of software would run on the CPU. Whenever we run into a portion of the code that is massively parallelized, we will pass the execution of that portion of the code to the device or the GPU. The host and device will basically talk to each other using via this channel called PCI Express bus. And the PCI Express bus, in our case, is going to be very slow relative to the host and device both. So the cost of exchanging the data between host and device is quite expensive. Therefore, the only portions of the code that we want to execute on device are the parts that are massively parallel, which is what CUDA is helping us do. So let's talk about threads. To utilize like this massive number of cores on the GPU, we want to execute CUDA kernels as a very large number of threads. And the GPU is designed to execute each kernel as thousands or even millions of threads, because that's what they are capable of. CUDA threads execute in a single instruction, multiple data fashion, commonly termed as SIM in the computer architecture language. And that is each thread executes the same instruction, but on a separate piece of data. The exact manner in which threads execute is slightly different from the precise definition of SIM model. NVIDIA calls their version of single instruction multiple data single instruction multiple thread, which is an acronym basically, but pretty much is the same idea with SIMD. To be precise, the exact difference between SIMD and SIMT is really not that important because the terms are just like thrown around in this CUDA language. So just think of these terms as having the same meaning for now. So another thing to note is that threads do not all execute at the same rate. Even though each thread is performing the same operation, the set of data being computed on in each thread is generally different, which can give rise to threads from the same kernel launch executing at different rates. So if you have multiple threads and they're not going to necessarily return at the same time or not complete their work at the same time. So in order to organize how threads are mapped to the cores on the CPU, on the GPU, CUDA has a hierarchy of threads. Now, this is one of the most important concepts in CUDA's programming model. And there are three levels in this hierarchy, and let's discuss each one of them. At the lowest level of the hierarchy, we have individual threads. We've already seen the threads, which is the execution of a kernel on a single piece of data. And pay attention to this because each thread gets mapped to one CUDA core on the GPU when the kernel or the GPU function is launched. In the next level up the hierarchy, we have a structure called a block. So sets of threads are grouped into blocks. When the kernel is launched, the blocks get mapped onto corresponding sets of CUDA cores, which will be covered now in the following slide. And at the highest level of the CUDA hierarchy, we have grids, which are basically collections of blocks. The entire kernel launch is executed as one grid, and that is mapped onto entire GPU and its memory. In summary, one kernel launch executes as one grid, which is mapped onto the entire device or the entire GPU. To keep these terms in order, I think it's going to be helpful to think of threads as elements of blocks and blocks as elements of grids, or as you can see right here at the bottom of the page, basically the threads are subsets of blocks and blocks are subsets of grids, and they are organized in a certain layout within each other. So each grid is composed of a set of blocks which are organized into either 1D, 2D, or 3-dimensional structures. So in this example, the block structure is composed of a 3x2 grid. So there are 3 blocks in the X dimension and 2 blocks in the Y dimension, giving us a total of 6 blocks in the grid. Similarly, blocks are composed of threads which are also organized into either 1D, 2D, or 3-dimensional structures. And in this same example that you can see on the slide, the thread structure is composed of a 4x3 block that is there. And there are 4 threads in the X dimension, and there are 3 threads in the Y dimension, giving us a total of 12 threads per block. So since this example has 6 blocks per grid and 12 threads per block, we have a total of 72 threads in the grid for this specific example. Or to put it another way, when we launch this kernel corresponding to this grid, there are a total of 72 threads that will be executing on the GPU concurrently, that will be serving us. Okay, so let's now take a look at how a CUDA program is organized in code. The biggest thing to remember is that the CPU is in control, right? By default, we always start with a CPU. So that is the host controls the entire flow of the program. The flow of the program begins just as a normal C program would begin with the main function. So sequential flow of the program occurs as normal until we reach a portion of the code that we want to offload onto GPU. So that is achieved through launching a kernel, which is executed on the device as a grid, as we discussed just now. So at this point, control of the program is immediately returned to the host. The main C function continues from the point directly after the kernel launch. the main function, and then continues to execute any serial code until we launch another kernel. One thing to note here is that the main C function does not wait on the kernel's completion. So if we need to gather the results from a specific kernel launch, we need to create an explicit barrier in the host code to tell the main C function to wait on the kernel's completion to continue. So we will also cover this barrier and how to basically put on this, all the threads in synchronization with each other in the coming weeks. So just to remember that the host code does not wait on the kernel's completion unless it's explicitly told to do so. So hopefully all of this makes sense. And now we will be looking more closely at each of these pieces of code and what this means and how we can break it down. So kernel launch syntax. Let's look at that. So kernel launch is just like calling any normal C function. The launch begins with the name of the kernel that we are executing, and parameters passed into the kernel are placed inside the parentheses. The only difference between a kernel launch and a function call is that we must specify the kernel's grid and block dimensions, which are passed into the kernel launch inside the triple brackets. So before we launch a kernel, we need to configure its launch parameters. How many blocks it's going to have, and inside each of its blocks, how many threads it's going to have. So the values of x, y, z in the parentheses are integer values. And I want to, again, sort of direct your attention here to the structure called dim3. So dim3 is a CUDA data structure that is simply a set of integers that correspond to a size, the size of the x, y, and z dimensions. So in the code shown here, the grid size and the block size are the dim3 data structure variable names. So you are basically, just to recap this slide, you have a grid. You want to specify what the size of the grid is going to be. You can either make it one-dimensional, so as one array. You can make it two-dimensional as a matrix, or you can make it three-dimensional, like a cube. And then you can specify in which direction how many units it's going to have. When you specify using grid size inside the brackets, you are essentially telling the GPU how many blocks you want it to have. And when you're doing the same with the block, you are telling how many threads you want to have inside each block and how do you want it to look, three-dimensional, two-dimensional, or one-dimensional. And then once you have specified those, right, like you see at the top, you can pass them into your kernel launch. So basically the kernel function that is going to be run on the GPU. So let's take another look at the same example and understand how to implement this kernel launch syntax. So we first configure the grid and block dimensions in this example. And in this example, the grid dimension is of the size 3 by 2. And the block dimension is of the size 4 by 3. So the same example that we talked about just previously. So when we launch the kernel with the specified configuration parameters, this is the illustration that we get. So this is the flow of the program to call a function that would be around the GPU. So, oops, let's take another look at the CUDA program flow. So one thing to remember, though we will be again talking about this in more detail, that the host and device have different memory regions. So in order to operate on any data inside a kernel, what we need to do first is to allocate memory on the device. So remember that in C, the way we were allocating memory was by using the function malloc. So now we are using this function called CUDA malloc, and what it does is it allocates memory in the memory of GPU for whatever amount or whatever number of bytes you want to use. Next, what we need to do is, excuse me, yeah. What we need to do is copy any relevant data into the device's memory or the GPU's memory region that we previously allocated that was in the host. This copying of data between the host and device is one of the most important and limiting aspects that that drives the flow of the CUDA program. Because as we talked about this previously, when you transfer data between host and device, it is pretty slow. So you want to be really careful with this operation. And next, you'll launch the kernel with a specific grid and block dimensions determined by the configuration parameters, like grid size and block size. And when you need to retrieve the results that are obtained from the kernel's execution, you have to copy the data back from the device to the host, like so. So we will talk all about these memory management concepts in greater detail, just to let you know beforehand. And please let me know if there are any questions so far. So let's talk about allocating device memory. So allocating device memory is going to be pretty similar to allocating memory in the language C. Recall that in the C, the function to allocate memory was malloc. The function to deallocate memory, right, after you allocate a certain memory, when you want to deallocate it, it was the function free. Similarly, to allocate memory on the device, we use the function CUDA malloc. And as you can see, CUDA malloc takes two arguments. The first argument is the memory location that we want to copy the data to on the device. And the second argument is the size of the memory region that we want to allocate. To deallocate memory on the device, we simply use the keyword CUDA free, and that just seizes the function and sets it free, and we are getting rid of all the basically memory that we allocated for it. Just going to keep it there for a few seconds. Okay. So to transfer data between the host and device, we're going to use this function called CUDA memcopy. CUDA memcopy is going to take 4 arguments. The first argument is a pointer to an address of the memory that we are copying into. And second argument, source, is a pointer to the address of the memory that we are copying from. And the third argument is the size of the data that we are transferring in units of bytes. And finally, the fourth argument is the direction in which we are transferring the data. So as you might guess, there are 2 possible directions that you might transfer the data in. If you're transferring the data from host to device, we basically set the direction argument to this keyword, which basically says CUDA memcopy host to device. And if you are transferring the data from the device to the host, you set the direction to CUDA memcopy device to host. So think of this as a string. It's not really a string, but it's a keyword. And in order to basically determine the direction, you are using one of these keywords. So there's an interesting example now. We're going to look at this example, and that will hopefully tie together all of the concepts that we have discussed up to this point. So we begin the program by stepping into the main function, right? Just like any C or C++ program. And now what we're going to do is we're going to define 2 variables that are pointers to integers. Now, since the host and device have separate memory regions, dereferencing a device pointer on the host would basically cause the program to crash. And in order to differentiate between host and device variables, what we're going to do is we're going to follow a naming convention that consists of preceding any variables that lives on the host with a letter H, and preceding the name of any variable that lives on the device with the variable with the letter D. And next, what we are going to do is we are going to allocate device memory using the function CUDA and we're going to pass in its two parameters. The first parameter in CUDA is a pointer that is pointing to the address of the memory that we're allocating on the device. The second parameter is simply the size of the memory region that we're allocating. So in a real program, there would have already be data stored in the host variable, even though we are not explicitly specifying it here. So let's just assume that HC, right, the variable that stores the data in the host memory or the CPU memory is already initialized with the data, right, in this example. So when what to do next is to use the CUDA memcopy to copy this data from the host memory into the device's memory. So the same basically configuration that we followed. You have the destination, you have the source. As you can see, the destination is the device variable and the source is the host variable, because that's how what the direction is going to be. And you are specifying the size of the variable, and the direction is specified as CUDA memcopy host to device. Yeah, there's a typo here because the zoomed in version shows device to host, but actually it's host to device. And we can understand it from by looking at the destination and source variables and where they stand and which arguments they correspond to. So what we do next is we set up the configuration parameters to specify the grid and block dimensions of the kernel launch. So in this example, the grid and block dimensions are both of the size 1 by 1 by 1, meaning there is only one block, and inside that one block, there is only one thread. And all of that is stored in one grid. So this is the configuration parameters that we're going to use. Then we can launch the kernel, right? We launch the kernel with these configuration parameters that we specified, and we are doing it inside the triple brackets, as discussed earlier. And what we do next is we pass into the kernel any arguments inside the kernel's parentheses. Note that the kernel launch in this example is executed as a single block containing as a single thread. So as a next step, what we're going to do is we're going to copy the results from the kernel launch back from the device onto the host using the function CUDA memcopy. And the direction is specified here correctly. It's from the device to host. So the source is DC and the destination is HC. And any guesses on what the next step should be here? Well, as a hint, I can say that so we are nearing the end. So exactly. We finally should deallocate any memory that we previously allocated. All right. We are doing it both for the host, right? And we are doing it for the CUDA. And we are just returning 0, just like we would do in any function. And that pretty much concludes the main function. So this is an example of a program flow in the CUDA programming language, or the platform really, showing how they usually go. So for example, let's think about some different cases now, right? A good example, and that's something we're going to discuss in the next lecture, is if you have a for loop, and a for loop is supposed to process 1,000 elements in an array. So provided that these elements do not have any dependency on each other, right? So one does not depend on the other being processed, or there's no any information flow or whatnot. Really, having a CPU, or like CPU is basically by default what all the programming languages use, do it sequentially doesn't really make much sense, because there is a really big potential there to use concurrency, to use parallelism. If you had, again, in theory, a GPU and you created a grid 10 by 10 by 10, right, with 1,000 threads, you could basically pass that for loop onto a kernel launch, or a function that is run on the GPU, and each thread would operate on one piece of data or one of the elements. And then what you would have is, instead of going one by one through the elements, you would have a potential to do whatever operation that you want to do in each of the elements all at the same time. So that is really the power of the CUDA. Previously, before CUDA was invented, in order to really utilize parallelism, like all these problems were sort of somehow returned into some graphics problem. But with the CUDA and the similar platforms, what we are able to do now is basically this ability to switch between GPU and CPU at any given time that we want, and basically look at the code, sort of determine by our architectural thinking, which part can be parallelized, and just follow this very simple flow, and potentially make your program 1,000 times faster. So 1,000 times or even more. Of course, it's not going to be perfect 1,000, because, as I said, there are some overheads we're running into as we are dealing with these with CUDA programming language. So sending the array information, like copying it into the memory in the GPU device, is a lot of overhead. Does take a little bit of time. And in the same way, retrieving whatever was basically obtained also takes time. Which is why it's important to use CUDA or the likes of it at the times when we can, but it's also important to profile your code and be able to tell and understand where it is useful, where it's not, and how it is helping you, if it's speeds up your code, and like be able to determine what the bottlenecks are in your program. So yeah, I think those are pretty much the points that I wanted to mention. So if there are any questions, we can go back to any of the slides that we have talked about so far. And yeah, clear up any of the confusions that might be caused here. Yes, please.
Why do we need to copy the data from the device back to the host? Like, is it possible to directly access the CPU?
No. Yeah, that's a really good question. So the question was for the online folks, why do we have to copy the data from host to device and back from device to host? Is it not possible to directly access the memory in the GPU or the device after it is done? And the answer for that is no, because if you are a CPU running program, and you are trying to access the memory of the GPU, you would crash. So that's why it has to be the computer would crash. So or the program would crash, really, not the computer. So that's why the transfer needs to happen in a safe way. And CUDA memcopy really provides that ability or that channel whereby you can do it. And on the architectural level, the reason why you need to do that transfer is because each one of them has their own dedicated memories. So like I hope you guys are able to see in this slide that there's a DRAM that's right under GPU that's that's located in the GPU, the graphics card, and there is the DRAM of the CPU of its own. And well, in the coming lectures, we will be seeing the global memory, local memory, how basically this memory is broken down into several categories. But essentially, the big idea is that each memory belongs to whatever component it lives on. And the information cannot be accessed from one to another unless you're using CUDA. Yeah. Yeah. By the way, just as a piece of information here, these lectures are meant to be really running for 1 hour. So this 1 hour, and we will be hoping the next week's CUDA lecture is also going to be 1 hour. So yeah, this all the content that we had for today is this. And unless there are any more questions, oh yeah, there is another question. Sorry.
Access the slide.
Yeah, I can share the slides later for sure. Are you guys in the UTMIST like Discord server? Yeah, okay. Yeah, in the Discord server we can definitely share that. And I'm gonna share this recording as well. So there's that. Yep.
How do we choose the grid and block dimension?
Oh, how do we choose that? Yeah, good question. So let's see where it was, which slide it was. Okay. So in this code, it says grid size. The grid size takes in two parameters, 3 and 2. What this means is we want to make a two-dimensional layout of the grid, and we want it to have 3 blocks in the X dimension, and we want it to have 2 blocks in the Y dimension. So 3 times 2, 6 blocks in total. We are specifying it using this grid size configuration parameter. And similarly, in order to specify how many threads we want each block to have, and each one of them is going to have their own number of threads, we are using block size configuration parameter, and we are passing on exactly 4 and 3, X size and Y size. And after that, we are just passing them into the function, kernel function.
Is that like 3, 2, 4, 3? Is there a convention or is it a design choice?
Very much design choice. Like just however many threads you want it to have. So there are some considerations, right? The difference between 1D, one-dimensional, or like one array of grid that has like blocks or side by side, and two-dimensional, like how are they different? So we're going to talk about it in the next lecture. But essentially, the idea is, so the way computer is going to see this is the first row, and then side by side, right next to it, there's going to be the second row. So if that makes sense, you're going to have block 0, block 1, block 2, and then block 0, 1 is going to follow from where block 2, 0 is located, right to the right of it, and then it will go. So essentially, they're all turned into arrays. And then, well, we're going to see some of the, like the concepts like memory call, like if we want to like access the memory, we don't want to do it in random locations. We want it to be sequential and whatnot. But yeah, those are all the topics of the next lecture. But yeah, that's a design choice, and there are some basically results associated with it, some consequences. Yeah. So thank you so much for coming. Hello.
So when you're assigning memory to the CUDA kernel,
Mhm.
how do you know how much memory to assigning? It's like what happens if we assign too much, assign too little? Is there some thought?
Yeah, so if you're gonna use more memory than what you assigned, the program is gonna crash. So there's gonna be an error. You basically know beforehand how much data memory you're gonna need and how much you're gonna assign. And that is how it is in the CUDA. Then, well, there are different layers of memory, and then that's again the topic of the next lecture. But it is gonna be basically assigned in the DRAM of the GPU, like shown in the blue box, and yeah, the very interesting, like important thing to do is when you write the kernel function to be around on GPU, you want to make sure that you're not exceeding whatever memory was allocated. So there are some safety precautions that we're going to take. There's going to be some if statements that we're going to use to make sure the index, for example, doesn't go over the size of the memory and whatnot. But yeah, well, if we exceed that though, we're going to crash. Yeah. Okay. That I'm gonna stop recording.